Hello everyone, welcome back. In this video lecture, we'll be solving this problem network delay time with the third approach, that is Dijkstra's algorithm. We have solved this problem using depth first search and breadth first search in the previous two videos, and I have attached the links for the videos in the description below. So make sure to check it out before you watch this video. So let's take a recap of the problem statement. So in this problem statement, you're given a network of n nodes labeled from 1 to n. You're also given times, which is a list of travel times as directed edges. That is, each element in the times array is a tuple u, v, w, where there is a directed edge from u to v having a travel time of w. We'll send a signal from a given node k, which is the source node, and we have to return the minimum time it takes for all the n nodes to receive the signal. If it is impossible for all the n nodes to receive the signal, in that case we return -1. Fine. In the input will be given the times array containing n tuples and a source node k from where the signal starts. And in the output we have to return one integer representing the minimum time taken by the signal to reach at each node. The range of k and n goes from 1 to 100, while each node is labeled from 1 to n, and there is no self edge for any node, while the time of travel from one node to another does not exceed 100. And all the UV pairs. Let's better understand the problem statement using an example. So here we have this example, which is the graph. It is a directed graph and the source node k is 2 in this case, and we want to find the minimum time for the signal which is starting at this node to arrive at all other nodes of the graph. We solved this problem using DFS first, then we solved this problem using BFS in the previous two videos, and I have attached the links for those videos in the description below, so make sure to check it out. In this video lecture, we'll be solving this problem using Dijkstra's algorithm. Let's see why Dijkstra algorithm will work here. So what do we want to do in this problem? We want to arrive at each node through the shortest path. That's our target. So this is our source node, which is node number 2, and we want to arrive at each node with the shortest amount of time, where this integer over each directed edge represents the time which we take from moving, which the signal takes from moving from source node to the destination node. So the problem turns into the single source shortest path problem, and we know that Dijkstra algorithm is used for solving such problems. Fine. So Dijkstra algorithm is a little different from BFS, although it is very similar. In Dijkstra algorithm we also use Q, but let's see how. So let's first see the answer for this particular graph. So you can see that to arrive at node number 1, the signal take 1 second. To arrive at node number 3, the signal take 1 second. And to arrive at node number 4, the signal take 1 plus 1 second. That is 2 seconds. And hence, out of all these times, 2 is the largest integer, or 2 second is the time in which the signal arrives at all the nodes of the graph. Hence, the answer for this particular test case is 2. So let's see how Dijkstra algorithm can be used to solve this problem. So here we have our graph which we will be using for simulating our Dijkstra algorithm for this particular problem. Okay, so we'll be using Dijkstra algorithm to solve this problem for this particular test case. So what is the difference between Dijkstra algorithm and simple BFS? They're almost similar. The only difference between BFS and Dijkstra algorithm is that the BFS visits the adjacent nodes of a particular node in a first in first out order. That means, let's say I start from node K, then I will push the adjacent nodes into the queue while performing my BFS. Then the nodes which I have pushed will be traversed in this first in first out order. So I can push B first, then I can push A, and in that case B will be processed first and A will be processed after that. Or vice versa is also possible, that I push A first, then I push B, and then I explore node A or pop node A from the queue, and then I pop node B from the queue. So there is no order in case of B. While in case of Dijkstra algorithm, we use a priority queue instead of using a simple queue, which simply sorts these edges according to the time. So while using priority queue, I'm sure that B will be popped first out of these two nodes. Why? Because the time taken to reach B from the node K is lesser than the time which the signal takes to move from K to A, because the time which the signal takes to move from K to B is lesser than the time which it takes to move to A. Therefore, B will be visited first in case of Dijkstra algorithm. So it simply sorts the adjacent nodes according to the time taken to reach them. Fine. How it will help and how it is better than the old BFS solution? It simply increases the chances of reaching the target node along the shortest path. That means I want to reach B, and there are two ways. If I explore this edge first, that is K to A, then to reach B, I will take 6 plus 2, that is 8 seconds. While if I explore this edge first, that is from K to B, then I will take simply 5 seconds, and hence this one is better. That's why the priority queue, which is used in Dijkstra algorithm, sorts these edges according to the time or travel time. Fine. So let's see the simulation of Dijkstra algorithm for this particular test. So this is my priority queue which I used to perform my algorithm, and this is signal arrived array. It represents the time for each node which the signal took to reach that particular node. So initially I push the source node along with the time which the source node took to which the signal took to reach the source node, and we know the signal took 0 units of time to reach the source node, because we are starting from the source node itself. Fine. So the first integer is the travel time, because we want our pair to be sorted by the first integer or the travel time, so that the node with the smallest travel time is processed first. So we pop this node from the priority queue and the source node is processed. Then we iterate over the adjacent edges, and we can see that we explore this B, and the time which the signal takes to move from K to B is 5 seconds, and 5 is less than infinity, hence it is updated to 5. Then I push this pair, that is the pair 5 and B, into my priority queue because I have processed this node. Then I will explore the second adjacent node, that is node A, and the time taken by the signal to move from K to A is 6 units, and 6 units is better than infinity. Hence, I update my signal arrived array for these nodes, for B and as well as for E. For B we get 5, and for A we get 6, and I push the pair 6A into my priority queue. Then in my priority queue, this will be the pair which will be explored first, that is the pair 5B, because the travel time for this node is least. So I will pop this pair out of the priority queue and I will explore the adjacent edges for node B. So what are the adjacent edges for node B? There is only one adjacent edge or node, which is this one, and let's try to update the travel time for A. You can see that the time which the signal take to arrive at node A through the node B will be 5 plus 3, that is 8, and 8 is a worse time than the already existing time for that particular node. Hence it is of no use to update the node with the new time. Fine. So this is removed from the queue while the time is not updated, because we already have a better time for node A. Then I pop the second pair from the queue, that is node A, which is this one, and I explore the adjacent nodes for this particular node, and we see there is only one such edge or node, which is this one, which moves to node B, and the time which the signal take to move to node B through the node A will be 6 plus 2, that is 8. And I can see that 8 is worse than the already existing time for node B. Therefore, it is of no use to update the node B with the new time. Hence, I leave it as it is. Fine. And now my priority queue is empty. My algorithm stops. And I have my signals arrived array prepared. And the maximum integer in this array will be my answer. That is 6. That means it takes 6 seconds for the signal to spread to the entire network. And that's my answer. Let's see the implementation for this algorithm. So this is the implementation for the given problem. So this is my graph, which is represented in the form of the adjacency list, and this is a network delay time function which takes in the times array, the size of the times array, or the number of nodes, and the source node. Then I iterate over the times array and I prepare my adjacency list here. So I push travel time first and then I push my destination. Since this is a directed edge, I'm simply pushing a one-way edge, that is from source to destination with the travel time. And this is my array which I initialize with a very large number. It will store the minimum time for each node for the signal to arrive. Then this is a Dijkstra function which takes in this signal received at array, the source node, and the number of nodes, and it simply prepares this signals received array, this particular graph. See the working of this Dijkstra algorithm. Here is the working of this Dijkstra algorithm. It takes in the signal received at array, number of nodes, and the source node. I declare a priority queue and I push source node and the time which the signal takes to arrive at the source node. So I push this pair into the queue and I simply set signal received at array for the source node to be 0 because it took 0 seconds to arrive at source node because I'm starting from the source node. Then I iterate till the priority queue is not empty. I simply pop the top element from the queue and the first element of this pair represents the travel time and the second element represents the node or the current node. Then I will check if the current node time, that is the time which we have here to reach the given current node which I extracted from the top of this priority queue, if that time is greater than the already existing time in my signal received at array, then simply I cannot optimize for this node and hence I continue because there is no meaning to update this array for the current node because I already have a better time. Okay, so then I traverse the adjacent nodes for the current node and I extract two parameters for the adjacent node or the neighbor node, that is the time. So this time represents the travel time to move from the current node to the neighbor node. Fine. And then I will check if the time taken to reach this neighbor node through this current node, which is calculated by adding the time for the current node with the travel time to move from the current node to the neighbor node here. If that time is smaller than the already existing arrival time for the neighbor node, in that case you can perform the relaxation here. So I perform my relaxation and I update the value of the time for the neighbor node with this new value. That is, it is better to arrive at the neighbor node through the current node. That's what I'm saying here. And I push the neighbor node into the queue for further process. Fine. So that's how the signal received at array is prepared. Here I can see that node which has the least travel time is popped first so that all the adjacent nodes to that node receive the signal fast. So that's what I'm trying to do in this algorithm. Let's discuss the time and space complexity for this algorithm. We know that the standard Dijkstra algorithm implementation takes n plus e log n time, where n represents the number of nodes in the graph and e represents the number of edges in the graph. And the space complexity for the given implementation is big of n plus e because I'm using a priority queue for performing the Dijkstra algorithm. Fine. So this is the solution class. This is my adjacency list which is used to store the graph This is my Dijkstra function, which takes in the signal received at array, source, and the number of nodes in the graph. This is my network delay time function, which takes in the times array, the number of nodes, and the source node, and returns an integer representing the minimum time. First, I build my adjacency list, which I declared here globally from the times array. So we have three things: a source node, which is the first element in this times array, destination node, which is the second element in the times array, and the travel time, which is the time which the signal take to move from source to destination. That is the third element in the times array. Then I make a directed edge from the source. Then I declare my signal received at large value. Then I call my Dijkstra function and pass in this signal received at array. Function will simply prepare this array for each node. Prepare this array. Then I initialize my answer with a very small value so that I can obtain the maximum integer from that signal received at array. That integer represents the minimum time for the signal to arrive at all the nodes of the network. So here I am checking if the answer is still a very large value. That means there is at least one node which is unreachable. In that case, I'm returning -1. Otherwise, I'm returning the answer. Here I declare a priority queue which sorts the pair of integers by the first integer. And I push the pair for the source node into this queue. Then I run my while loop till the queue is not empty. As I do in BFS, I extract the top element from the queue, and the priority queue sorts the elements by the first integer or the travel time. That means the node which has the least travel time will be popped first. Then here I'm checking if the current node time is greater than the signal received at time for the current node, that is the time which we already have for that node. In that case, there is no scope for the relaxation and we continue to the next. Otherwise, we want to broadcast the signal to adjacent nodes because it is better to reach because the current node time is smaller than the time which we already have for the current node. In that case, we want to broadcast the signal to adjacent nodes. That is, we are saying that the signal will arrive faster the adjacent nodes through the current. Fine. So I traverse the adjacent nodes and I check if it is better to reach the neighbor node through the current node. If it is the case, then I perform the relaxation. Fine. And I push the new value for the neighbor node, new value of travel time for the neighbor node along with the neighbor node into the priority queue. Fine. In this fashion, I will have my signal received at array prepared, and finally I'm returning my answer right from here. So this is how the Dijkstra algorithm is working. So if you have any doubts in understanding this implementation, then I would recommend you to understand Dijkstra algorithm first and its working. Then you will understand this algorithm in a better way. And I will also recommend you to watch my previous two videos for the same problem to get a better idea of the problem state. Let's see the implementation in other language. So this is the implementation in Java. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.